this video is going to talk about multivalent metals in ionic compounds and how to name them. The valence of an atom is the charge that it takes on when it's in a bond. So for example, if I had lithium oxide, Li2O, those lithiums would have a charge of +1 each, so its valence would be +1. The valence of oxygen in this compound is 2-, would be -2. So it's the charge that is taken on in a bond. Some metals, due to complications with their inner atomic structure, or the transition metal specifically, can take on more than one valence in different situations. Copper, for example, Cu, in compounds sometimes appears as +1, and sometimes he appears as 2+. What's a 2? 2+. There we go. And the reason that happens has to do with some more complex model of the atom that we haven't covered yet, but the bottom line is he's able to do it. We only really look at this multivalent for metals because almost all of the non-metals will act as multivalent atoms or will form different charges in different situations. So this is really, when we say something's a multivalent metal, that's special because that's one of those transition metals most of the time. The group 1 and 2 atoms like lithium, sodium, calcium, magnesium, those guys are almost never multivalent. So if we deal with these first two categories, they're not multivalent. The multivalent ones are the transition metal ones. And again, there's complex reasons for that we haven't studied yet. What that means, though, is when we name these compounds, we need to make sure we identify which valence is in the compound so that we can tell the two different things apart. For example, if this, in the first example here, copper chloride, we would have to say, is that copper 1 chloride or copper 2 chloride, so that we can keep the two things separate from each other. So how are we going to do this? First, we're going to identify if the metal itself is multivalent or not. Well, some transition metals are, but not all, so don't just assume it is. You have to look in the periodic table to find out if it is or not. We write the name of the metal, just like we usually do, and then in brackets after the metal, if it is multivalent, we put the valence in Roman numerals. If it is not multivalent, then we do not include the brackets in the Roman numerals. It's only for ones that can take on more than one charge. Finally, we include the non-metal, changing the end of the non-metal to IDE like we have all along. So example number 1 here, copper chloride. So we would have copper, and we have chloride. And I can imagine going to my periodic table and seeing that copper could be copper 1+ or copper 2+. So I know it's multivalent. So then if I imagine reversing the crossover, and I look at this particular compound, I can see in this case, this copper was 2+, so this is the valence that occurred here. And so I indicate that in brackets in between the two, the metal and the non-metal. So this we would say copper 2 chloride. So then again on the I look up for the next example. Fe is iron. And if I look them up on the periodic table, I'm going to see iron could have been 2+ or 3+. So I know it's one of these ones that I have to specify, so I put my brackets in. Oxide. Now, it's Fe2O3. So I imagine reversing my crossover. Oxygen is a 2- and iron is a 3+. So for this particular compound, it was the 3 valence for iron oxide. Iron 3 oxide. Last one, and careful here, might seem simple, but there's a trick. Copper oxide, and because I know that copper is one of my multivalent ones, I know I need to put this in. Now if I just looked at this compound, CuO, and I reversed my crossover, I might have thought it was 1 and 1, and so I might want to say this is copper 1. But if I think a little bit more carefully, I'll remember that oxygen itself has a valence of 2-. And what I know is it ended in a 1-to-1 ratio. So if I imagine reversing my crossover, what number must have occurred up here to get back to a 1-to-1 ratio? If I think of it that way, hopefully I'll recognize that it should have been 2 plus. And so this is actually copper 2 oxide. So remember, when we do our crossover with ionic compounds and then we have the numbers on the bottom, the next step is to reduce. So if I'm thinking about going backwards from my crossed over compound to my original name, I have to remember that I may have reduced in the past, and I need to be careful to make sure that I get the right valence. We can also use these names to predict the compounds. So here we go. Tin is SN. Oxide, this one would have been 2 plus, this one would have been 2 minus. So I'll cross them over. I get 2, 2, which I can reduce to tin oxide, 1-to-1. Lead 4 chloride, Pb, Cl. If I look up Cl on the periodic table, I see 1 minus. Lead 4, so I don't have to look it up. It tells me right there. I cross them over, and I get PbCl4. And finally, copper 1 bromide. So copper, I told you it's 1 plus. Bromine, if you look them up, he's 1 minus. Cross them over, and you get CuBr. So that's how we use the names in the specified valences, or how we specify the valences to name them. We have to specify because some metals are multivalent, which means they can take on different charges when in compound than what we would expect or than what we would see most of the time. There's also a secondary naming system for this. So this is the standard now, but a while ago they wouldn't have said this. They would have used words like cuprous and cupric, where one of these would correspond with copper 1 and the other one would correspond with copper 2. What I suggest is, if you ever run across these names, that you use the internet to get the proper IUPAC name, and then you'll be able to go from there. It's not worth memorizing all these because hopefully it's an outdated system, but in a situation where you're looking up a chemical name, you might be surprised to see something like this. These things are making reference to the valence, so all you have to do is use the internet to look up which valence, whichever one means. So that's how you name multivalent metals, or multivalent ionic metals in ionic compounds. There we go.